In these examples, we are going to use separation of variables in order to solve these differential equations. So in our first example, we have the differential equation y prime is equal to 2x divided by y. The first thing we want to do is separate variables, which means that we want every term that has a y to be on one side of the equation and only everything with an x on the other side of the equation. So we want to separate the x's from the y's. So I'm going to multiply both sides of this equation by y so that I have y prime and y on one side of the equation, and on the right side of the equation we only have x. Now that we've separated variables, we are going to integrate both sides of the equation with respect to x. So I'm integrating both sides and I'm adding a dx on the end. So we have y prime. I'm going to switch the order that I write these in on the left. In the left integral, I'm going to write the y first and then the y prime. So I have the integral of y. I'm going to replace y prime with dy dx. And then I have a dx on the end of that. And on the right, we still have just the integral of 2x dx. So I did that so we can see that the dx is canceled, and we're left with the integral of y with respect to y is equal to the integral of 2x dx. I'm going to integrate y with respect to y, and that's going to give me 1/2 y squared plus c, because we increased the exponent by 1 and divide by the new exponent. On the right side of the equation, we'll increase the exponent by 2 and divide by the new exponent. There was already a 2 there, so those 2's will cancel, and we get a plus c. So I have 2 plus c's, but it doesn't matter. I could truly just write one of them, because if I combine the two constants, we're just going to have one constant overall. So I really don't need to write that plus c right there. So I have 1/2 y squared is equal to x squared plus c. Now I'm going to just get the c isolated on one side of the equation, which leaves me with this equation here. Notice that our solution to that first example does have a c in it because we were not given an initial condition, so we were not asked to find a particular solution. So in our answer there, we're giving a family of solutions. In the second part here, we're looking for the function f of t that goes through the point 0, 10. So here we do have an initial condition given to us. So we will eventually find a particular solution here. So I'm going to start with the differential equation. And I'm going to separate variables, so I'm going to get everything with a y on one side and everything with a t on the other side. So to do that, I'm going to put all my y's on the left side of the equation. I'm going to divide by y on this side, same as multiplying by 1 over y. So right now I have 1 over y dy is equal to 1/2. And that dy is still divided by dt on the left side. And I want to move that dt to the right side of the equation. So I now have 1 over y dy is equal to 1/2 dt. And now I'm going to integrate both sides of this equation. The integral of 1 over y dy is natural log absolute value of y. I could write the plus c here. I'm not going to. I'm going to choose to write the plus c on the other side of the equation when I integrate 1/2 with respect to t, which will leave me with 1/2 t. And there I will add my constant of integration. Now we're told that this function should satisfy the initial condition that when x is 0, or when t is 0, y is equal to 10. So I'm going to now plug in 0 for t and 10 for y, which will give me natural log of 10 is equal to 1/2 multiplied by 0 plus c, which tells me that c is equal to natural log of 10. So now I can rewrite my solution as natural log absolute value of y is equal to 1/2 t plus, instead of writing c, we just solved for c, we found that c was natural log of 10. So here in example 2, we want to write and find the general solution of differential equations that model the given statements. So in part A, we start off with the rate of change of g with respect to x. That means the derivative of g with respect to x, so that is dg dx. Then they tell us that is means equal sign. Proportional to means we're going to have to introduce a constant of proportionality, and it is proportional to the cube of x, and the cube over x is written as x cubed. That proportional to is just a constant for x. So now we want to solve this differential equation. We're going to separate variables, so I'm going to multiply both sides of this equation by dx so that cancels, leaving me with dg is equal to kx cubed dx. Then I will integrate both sides of this equation. The integral of dg is just simply capital G. And then on the right side, the integral of kx cubed, I'm going to increase my exponent by 1, so I now have x to the 4th. And I'll divide by my new exponent of 4. The constant of k stays in front, and we have our constant of integration c. So we have found that the function g of x is equal to k x to the 4th divided by 4 plus c. In part B, they tell us that the rate of change of p with respect to t, so we start off with dp dt, just turning these words into mathematical symbols, is an equal sign, inversely proportional to 3 minus t. So here we have inversely proportional, so we're still going to have a constant of proportionality. So I'll still use k as my constant of proportionality, but when they say 3 minus t, because it's inversely proportional, I'm going to need to put the 3 minus t in the denominator. So there is our differential equation. So now let's go ahead and separate variables. I'm going to multiply both sides of this equation by t. I want my t's separated from my p's. So here we have this differential equation now. I'm going to integrate both sides of it now that we have the variables separated. On the left side, the integral of dp is simply p. On the right side, to integrate k divided by 3 minus t, I'm going to need to use u sub. I'm going to let u equal 3 minus t, which means that my du is a negative dt, which I don't have in the integral, so I'll manipulate that to say that a negative du is equal to dt. The k that's in the numerator of the integral can be pulled on the outside, so I'll just pull the k out. I'm going to replace dt with a negative du, so I'll put a negative sign out there and then a du at the end of the integral. And this 3 minus t that's in the denominator, that's just a 1 over u. So we're just integrating negative k with the integral of du over u. And the integral of du over u is natural log absolute value of u plus c. So I will go back and plug in what u was. So I have natural log absolute value of 3 minus t plus c. So we found that the solution to this differential equation is the function p of t equals k multiplied by natural log of 3 minus t plus c.